Hi everyone, in this video we're going to look at the 2018 physics exam. If you haven't already seen the 2017 video, go and watch the first little bit of the first video, and that's where I talk a little bit about the structure and just the instructions here. Otherwise we're going to get straight into it. Question 1. Use the following information to answer questions 1 and 2. A wire carrying a current of 10 amps is placed in a uniform magnetic field of strength 4 times 10 to the negative 4 Tesla as shown below. 10 centimeters of the wire is in the field. So that's here. Question 1. Which of the following best gives the magnitude of the force acting on the wire? So we have a wire with a current going through it, perpendicular to a magnetic field going out of north into south. And when that happens, when you have a perpendicular component of current in a field, there's a force. And the direction of the force is given by the right-hand slap rule, right-hand palm rule, whatever you want to call it. And it looks like that's what we're going to do in question 2. But question 1 wants the magnitude of the force. So we have a simple formula for this. It is F equals N B I L, where N is the, how many wires are bundled together. This just says a wire, so we can assume N equals 1. B is the magnetic field strength given to us, I is the current given to us, and L is the length of the wire that is in the field. That's also given to us. So it's 1 times 4 times 10 to the negative 4 times 10 amps for the current, and times 0.1 meters for how much wire is in the field. That's 10 centimeters. Okay, so calculate that. So we've got 1 times 10 times 0.1, all of that cancels out, just becomes 1. And we're left with this 4 times 10 to the negative 4. So the answer is B. Okay, if you're not confident doing that in your head, then just use a calculator. Question 2, which one of the following best gives the direction of the force acting on the wire? So this is where we use our right hand slap rule. So I'll draw a crude picture of a hand just to make sure you know what you're doing. So right hand, my thumb would be on top like this, and my fingers would be like this. Okay, and then that's my palm. Okay, stupid drawing, I know, but gets the point across. So what we do in these kinds of situations is you let your thumb point in the direction of the current. So in this case it's going to be pointing upwards. You let your fingers point in the direction of the magnetic field, so that's going to be left, from right to left. It's coming out of north and into south. Okay, like this. And so your palm will give you the direction that the force will be applied on that current. And so that to us looks like it's coming out of the page. If you stick your hand in front of you and set everything up, thumb pointing up, fingers pointing towards the left, your palm will be facing you, and for us that's out of the page. Okay. I'll periodically check the exam report just to make sure we're not screwing things up too much. So far we're all good, and the majority of people got those questions right. Alright, question 3. A straight wire carries a current of 10 amps. Which one of the following diagrams best shows the magnetic field associated with this current? So we've got a current in a wire that's going upwards, and it creates a magnetic field. Okay, moving charges, which is what current is, create a magnetic field. And just based on knowledge of the theory, that magnetic field will go in a circular direction around the wire, and that is given to us by the right hand grip rule. So you stick your right hand in front of you, point your thumb in whatever direction the current is flowing, and curl your fingers. Okay, and if you're doing that right now, your fingers should curl around the back of that imaginary wire and around the front. So your fingers go to the left around the back and then curve to the right around the front. So that's going to look like option A. Okay? So the right hand grip rule. Question 4. A small sphere has a charge of 2 times 10 to the negative 6 coulombs on it. Take K equals 8.99 times 10 to the 9. The strength of the electric field due to this charge at a point 3 meters from the sphere is best given by. So what's the question asking for? Strength of the electric field. and this is due to a point charge, okay, or a sphere of charge. Alright, so we've got a formula for this. This is E equals K times Q over R squared. E is the electric field strength, K is this Coulomb constant, Q is the magnitude of the charge, and R is the distance we are from the charge in meters. So putting all our values into there, we get 8.99 times 10 to the 9. The charge is 2 times 10 to the negative 6, and we are 3 meters from that charge, so 3 squared. Let's get our calculator out. Okay, 8.99 times 10 to the 9 times fraction 2 times 10 to the negative 6, and 3 squared is 9. So I get close to 2,000, and that looks like it's going to correspond there to option D. Alright, let's get rid of that. So option D is the correct answer. Question 5. 4 students are pulling on ropes in a 4-person tug of war. The relative sizes of the forces acting on the various ropes are all of these. The situation is shown in the diagram below. Which one of the following best gives the magnitude of the resultant force, highlight that, acting at the center of the tug of war ropes at this point here? So this is just a classic force problem. So it's forces in 2 dimensions. We just have to work out the net force acting on that bit in the middle. So we're going to look at the forces vertically, look at the forces horizontally, and then sort of combine them vectorially for an end resultant force. So let's look at the I guess the vertical forces here. So Fw and Fy. So Fw is 200, Fy is 180. So combining those 2 vertical forces, you know, we'll get an upwards force of 20 newtons. The horizontal forces Fz, so 210, and Fx is 240. So combining those 2 forces, we'll get a rightwards force of magnitude 30 newtons. Now we've got to combine these 2 forces like so. And so the resultant force would be this blue arrow here. Okay, and this is just a right angle triangle. This is 30, this is 20. Our job is to work out what the length of that arrow is, so we're going to use Pythagoras theorem here. So that unknown net force is equal to the square root of the other 2 sides squared. And quick calculation, let's have a look. So square root of 30 squared plus 20 squared. There we go, close to 36, 36.1. So we're going to say that's option C. Alright. Okay, so question 6. Lisa is driving a car of mass 1,000 kilograms at 20 meters per second when she sees a dog in the middle of the road ahead of her. She takes 0.5 seconds to react and then brakes to a stop with a constant braking force. Her speed is shown in the graph below. Lisa stops before she hits the dog. I guess they have to put that in there, otherwise it might be a bit morbid. Anyway, here's a graph of her speed over time. Which one of the following is closest to the magnitude of the braking force acting on Lisa's car during her braking time? So let's think about how we might need to work this out. So force, our job is to work out a force. Now force is linked with mass and acceleration. So we've got the mass of the car, but we need to know the acceleration of the car during this time to then be able to work out the force. Now we've got a speed versus time graph. So we know that from speed versus time graphs, the gradient of the graph is the acceleration. Okay, so if we look at the gradient here, the rise would be, I guess, negative 20 over a time of 2.5. Just be careful because that she doesn't start braking until that point there. So this time, the run, I guess, is 2.5. Right, so how many times does 2.5 go into 20? So 2, 4, 6, 8. It's negative 8 meters per second squared, assuming that she's traveling in the positive direction. But we only care about the magnitude, so don't really worry about the negative there. Alright, now the force is mass times acceleration, or 1000 times 8, which is 8000, which matches 8 kilonewtons there. So question 6 is option C. Question 7. At one point on Earth's surface at a distance r from the center of the Earth, the gravitational field strength is measured as 9.76 newtons per kilogram. Which one of the following is closest to Earth's gravitational field strength at a distance 2r above the surface of the Earth at that point? So this is a really sort of sneaky question, so I'm going to draw the picture. So here's the Earth, there's the center. This we're going to call the distance r, okay, because I think they're trying to get you to note that that is, g at the surface of the Earth, g equals 9.8. But now they're claiming that we are a distance 2r above the surface of the Earth. So that's an additional 2 r's, like that. So in total, we are a distance of 3r from the center of the Earth. So what's happened is we've tripled our initial distance. Okay. Now, due to the inverse square law, the gravitational field strength is inversely proportional to the square of the distance, which means if we triple the original distance, then our gravitational field strength becomes 1 over 3 squared of the original gravitational field strength. So all we've got to do is what's 1/9 of the original field strength? 9.76. Okay, 1/9 being 1 over this 3 squared. Okay, so that is about 1.08. Don't really have to use a calculator there, you can just sort of eyeball it here, because 9-ish or so divided by 9 is around 1. Right, if you want to be careful, I guess you can calculate it very quickly. Where's my calculator? Here it is. Okay, so 1 over 9 times 9.76. There you go, 1.08. Okay, next two questions. Question 8. A railway truck X of mass 10 tons moving at 6 meters per second collides with a stationary railway truck Y of mass 5 tons. After the collision, the trucks are joined together and move off as one. The situation is shown below. Okay, so this truck comes in, this one's stationary, smacks into it, they click together and they move off in that direction again. So question 8 is the final speed of the joined railway trucks after the collision is closest to. Alright, so this is a classical momentum question. So we're going to set up our momentum equation. m1u1 plus m2u2 equals, and because they join together, you can treat it as a combined mass with a common velocity v. Our job is to work out v. So v is m1 plus doing it the wrong way around, m1u1 plus m2u2 over m1 plus m2. Okay, so we just chuck all our numbers in there. Let's do it very quickly. So the first cart is 10 tons, so that's 10,000. I'll just write 10,000 times its initial speed, which is 6, plus the next truck has a mass of 5 tons, but it's not moving, so that's speed is 0, and their combined mass is 1,500 kilograms or 15 tons. So quick calculation, we're going to get, just make a note that disappears, we don't have to type that in. Okay, so 10,000 times 6, you could probably do this in your head actually. 10,000 times 6 is 60,000 divided by 15,000, it's going to give me 4. There you go. So they move off at a speed of 4 meters per second. Question 9. The collision of the railway trucks is best described as one where, and we've got a bunch of options here. So, kinetic energy is conserved, but momentum is not conserved. Well, this seems to be a closed system, an isolated system with no external forces. So we can immediately rule out any that say momentum is not conserved, so it can't be A. Kinetic energy is not conserved, but momentum is conserved. Maybe, we'll check in a second. C is wrong because it says momentum is not conserved. So it's either B or D. So it's basically asking us, is kinetic energy conserved or not, right? Or another way to phrase that, is it a elastic or an inelastic collision? Now, just be aware that anytime two objects stick together after colliding, it's always inelastic. So you don't have to actually calculate it here. It's a multiple choice question. Okay, so kinetic energy is not conserved, but momentum is conserved because it's an isolated system. You can, of course, double check if you want to, but I'm telling you 100% that anytime two objects stick together after colliding, that it is not an elastic collision. Can't be. Okay, question 10. A loudspeaker is producing a sound wave of constant frequency. I'm just going to pause for time here. What are we up to? 16 minutes. Okay, we're going good. Let's start that one again. So, question 10. A loudspeaker is producing a sound wave of constant frequency. Consider a tiny dust particle 1 meter in front of the loudspeaker. So there it is. Which one of the following diagrams best describes the motion of the dust particle? So I guess this question is trying to get you to recall what type of wave that sound waves are. So sound waves are longitudinal wave, which means the speaker it's got this little diaphragm inside which sort of goes back and forth like this, and it sort of creates regions of varying pressure in the air just in front of where that diaphragm is, and that pressure sort of propagates through the air, and that's what sound is. Okay, so all the air particles are moving in the same direction as this diaphragm, which is back and forth like this, or left and right from our point of view. So the dust particle will be moving left and right. So the best one that matches that is option D. Question 11. Alex hears the siren from a stationary fire engine. Compared with the sound Alex hears from the stationary fire engine, the sound Alex will hear as the fire engine approaches him, will have increased what? Okay. So let's just look at the options and see which one makes the most sense. So the speed of the sound will increase. No. The speed of the sound in air is fixed. If there was like wind or something, then you could maybe make an argument for that, but it didn't say anything about that. So the speed of sound in air doesn't change, whether or not there's a fire engine moving towards you or not. So it can't be A. The period of the sound wave. Well, I'd say no, only because I know what the answer is going to be. The period is linked in with multiple different factors here, so it depends on the frequency, of course, but it also kind of has a dependency on the speed and the wavelength as well. So we're not going to say it's period. Here's an interesting thing though, the amplitude. Okay, so the perceived, I guess, loudness of the sound, sure, that may increase because the fire engine is coming towards you, it's just closer. So amplitude is actually a correct answer here, but I'm pretty sure whoever wrote this exam was expecting people to say frequency because they're setting this up as like a Doppler effect question. Okay, so when a sound source moves towards you, the perceived frequency is higher than what it would be if it was stationary. Okay, that's just Doppler effect. But I think option C is actually also correct, and I'm pretty sure that the examiner's report will say as such. So let's double check this. Where am I? Okay, so the examiner's report, don't want to scroll too far because I don't want to know what the answers are. Okay, so, yep, both options C and D were accepted. So there you go. Alright, so most people answered with D. I think that's what the expected answer was, but the examiners were probably like, oh crap, we shouldn't have put amplitude in there because that's also a correct answer. So yeah, that's that. Question 12. A teacher sets up an apparatus to demonstrate Young's double slit experiment. A pattern of bright and dark bands is observed on the screen as shown below. So there's a laser going through double slit, get that classical interference pattern there. Which one of the following actions will increase the distance delta x, so the distance between dark bands, in this interference pattern? So what can we do here to increase this delta x? Well, luckily for us, we've got a nice formula that gives us delta x, which is wavelength times distance to the screen divided by slit separation. So varying any one of these things in a particular way will increase x. So we could either increase the wavelength, increase the distance to the screen, or decrease the separation of the slits. So that seems to be option C. So we're going to say option C. Let's double check the other ones. Decrease the distance between the slits. No, because decreasing L will decrease X. Decrease the wavelength. No, because decreasing wavelength will decrease X. Decrease slit width. This equation's got nothing to do with slit width, so the best option there is C. Question 13. Which one of the following diagrams best represents the graph of the Lorentz factor gamma versus speed for an electron that is accelerated from rest to near the speed of light c? Okay, this is an interesting question because it requires you to understand the, limitations of the Lorentz factor. So let's just have a look at the graphs and see which one is the most correct. Now, it is true that the Lorentz factor value shoots off towards infinity like this, asymptotically, as you approach the speed of light. However, the Lorentz factor cannot have a value less than 1. Okay, because if you go and write in, like, if you're stationary, right? So if you're stationary, your velocity is 0. Okay, what does this turn into? Well, it turns into 1 divided by square root of 1 minus, this is just 0, so square root of 1 is 1, so that's just 1. Okay, and even if you have a negative velocity in there, the fact that we're squaring this gets rid of that negative. So the smallest possible value of gamma is 1. Okay, so it can't be A, can't be C. That's just not what the graph looks like. Okay, it shoots off asymptotically like this. So it can't be B, so the only correct one there is D. Okay. Question 14. Which one of the following statements about the kinetic energy EK of a proton traveling at relativistic speed is the most accurate? Alright, so let's just have a read and think about what each one means and its merits. So the difference between the proton's relativistic kinetic energy and its classical kinetic energy cannot be determined. The difference between the proton's relativistic kinetic energy and its classical kinetic energy. Well, I mean, if it's talking about like numerical difference, well, that's wrong because we've got formulas that allow us to calculate those two things. So I don't think it's A. B, the proton's relativistic kinetic energy is greater than its classical kinetic energy. That one sounds like it's going to be correct, so I'll keep reading. The proton's relativistic energy is the same as its classical, or the proton's relativistic energy is less than its classical. Okay. So, how can we sort of prove what's going on here? So, well, I guess one thing we could do is write down the formula for the kinetic energy of a relativistic particle. Now, I can't remember what it is, so I'm going to use my formula sheet. It is gamma minus 1 times mc squared. Okay. Alright. Now, let's just think about what this equation is compared to the classic kinetic energy formula, half mv squared. Okay, now assuming that nothing can go faster than the speed of light, then this thing has an upper bound. Okay, if you throw in the speed of light in there, that's the maximum possible kinetic energy you could have if you're talking about classical kinetic energy. So there's like a maximum number here. But the relativistic equation, the closer and closer you get to the speed of light, the larger and larger this value keeps getting. Okay, and you can't get to the speed of light, but the closer and closer you get, this thing shoots off towards infinity. Okay, so this can become as arbitrarily large as you need it to be to then make it larger than this number here that you would get. Okay, so I'm going to say it's B, only because the Lorentz factor can be made as large as you like just by making the proton move faster and faster. Okay. All right, question 15. When a beam of particles such as electrons passes through a narrow slit, diffraction effects can occur as shown in the diagram below. Okay, so that's your classical, I say classical, it's your classic single slit electron diffraction experiment. This phenomenon can be described by Heisenberg's uncertainty principle because when the electrons pass through the slit, the uncertainty in there, and we've got some options. Okay, so the uncertainty in their y position does not affect the uncertainty in their y momentum. Well, that's wrong because Heisenberg's uncertainty principle looks like this. Okay, don't worry about the x. You could interchange it with y if you need to. Okay, so assuming that you want this relationship to hold, eventually you'll reach a point where varying this needs to vary this as well. So the y position, the uncertainty in the y position would affect the uncertainty in their y momentum. B, y momentum affects the uncertainty of their x momentum. No, okay, because there's only one type of momentum in there. X position affects the uncertainty, so uncertainty in their x position affects the uncertainty of their x momentum. Well, that would be true if the directions were swapped around here. Or D, the uncertainty in the y position affects the uncertainty in their y momentum. Well, I'm going to say it's option D because that follows the way that the directions have been set up in this scenario. So this, like the slit width here, that up and down direction, that sort of telling us the uncertainty in the y position as they're going through the slit, and then they spread out anywhere in this range. Again, that's an up-down direction, which is the y direction here, so that's corresponding to their uncertainty in their y momentum. So I'm going to say option D. Yeah, I think that's it. Question 16. Polarization is a property of what? All types of waves, only sound waves, only transverse waves, only longitudinal waves. Well, the answer there is C. Okay, only transverse waves can be polarized, longitudinal waves can't be polarized, sound is a longitudinal wave, and it can't be all types of waves because longitudinal waves can't be polarized, so it's, the best option there is option C. Question 17. The results of a photoelectric experiment are displayed on the graph below. The graph shows the maximum kinetic energy of photoelectrons versus the frequency f of light falling on the metal surface. So this is your kinetic energy versus frequency graph. There's that nice straight line that we are familiar with. A second experiment is conducted with the original metal surface being replaced by one with a larger work function. The original data is shown with a solid line, and the results of the second experiment are shown with a dashed line. Which of the following graphs shows the results from the second experiment? Okay, so let me just quickly prime everyone. Okay, that's kinetic energy, max kinetic energy, frequency. You get a graph that looks, I'll just draw a straight line there, something like that. Okay, this value here, where it intersects the y-axis, the negative of that is the work function. So I'll just say negative work function there. Okay, so that was, if that was -2, then the work function would equal 2. Okay? If you have another graph, do it in green, and it shifts its position like this, that might be -3. So the work function for that particular metal would be 3. Okay? So a metal with a larger work function will produce a line that is shifted down, okay, translated down from the original line. Alright? And it would have the same gradient, because the gradient is telling us what Planck's constant is. So it's going to be, if you imagine continuing this line down, where does it intersect the y-axis? It intersects at a lower point. Okay, so I'm going to claim that the answer there is A. Okay, can't be C or D because the gradients don't match, and it's not B because this dotted line looks like it's been shifted up from the original solid line, which we know is wrong based on what I just said. So it's option A. Question 18. The experimental uncertainty in a measurement of any particular quantity is best described as a quantitative estimate of the doubt associated with the measurement. That sounds good. I'm going to just put a mark there for now. Let's read the other ones though. The degree of confidence a scientist has in their experimental technique. No. I like A better. The difference between the measurement and the true value of the quantity. No. The result of one measurement, repeated measurements can eliminate uncertainty. Okay, so I'm going to stick with A. So it's a quantitative estimate of the doubt associated with the measurement. And that sort of best describes like the definition of uncertainty when we're talking about measuring devices and how we allocate uncertainty based on the, I guess, precision of our measuring device, or like how, I won't say precision, I'll say like what the resolution of our measuring device is, right? So if your measuring device measures, let's say you're measuring length, you measure, say, with a ruler that has centimeter increments, you can only be as sure as half a centimeter from the increment point. Okay, that's your plus minus half a centimeter. But if you're measuring something with a ruler that has millimeter measurements, then your uncertainty would be half a millimeter, plus minus half a millimeter, because you're able to read that value more accurately, and you're less doubtful of what your actual value is that you're measuring. So that's what A is talking about. Okay, so I'm going to go with A. B is not quite the same thing. That's sort of like whether or not you think the way that you're doing the experiment is right. It's got nothing to do with measuring and being confident of your measurement, right? So it can't be B. C, the difference between the measurement and the true value of the quantity. That's not uncertainty. That's sort of more just like a how accurate your data is. And D, the result of one measurement, the repeated measurements can eliminate uncertainty. Repeated measurements can eliminate random error, but they won't necessarily eliminate uncertainty because, again, your uncertainty is related to the resolution of your measuring device. So it's not D. So I'll stick with A. Question 19. The diagram below shows a properly calibrated... Start again. The diagram below shows a properly calibrated ammeter with its pointer registering a current of close to 3 amps. That's there. Which one of the following is the most appropriate measure of the uncertainty of this pointer reading? Well, we were just talking about this. So the resolution of your measuring device, which in this case is 1 amp, everything's marked off in 1 amp increments, we can only be as certain of our measurement by half an amp, because that's half of the divisions of our measuring device, half of the divisions of the ammeter here. So I'm going to say it is B, because that is just the definition of how you get your uncertainty from your measuring device. Question 20, last one for multiple choice. A group of physics students conducts a controlled experiment to investigate the phenomenon of electromagnetic induction. The students place a coil within a uniform magnetic field as shown in the diagram below. Cool, so here's a coil attached to, that looks like a split ring commutator, and it's hooked up to an oscilloscope in between two magnets there as well. The coil is spun at 50 revolutions per minute, 100 revolutions per minute, and then 150 revolutions per minute, and the peak EMF is measured each time on an oscilloscope. Which of the following best identifies the independent and dependent variables and a possible controlled variable in this experiment? Okay, so just remember, your independent variable is what you are physically changing yourself. Okay, your dependent variable is what you are measuring that is due to changing the independent variable, and the controlled variable is just something you don't change at all in the experiment. You try and keep it as constant as possible. So let's just think about that for a second. It says the coil is spun at 50 revolutions per minute, then 100, then 150. So we're changing that ourselves, and then we are measuring the peak EMF. Okay, so the independent variable looks like it's the speed of rotation here, and the dependent variable looks like it's the peak EMF. Okay, so the only one that matches that those options is B. And just check the controlled variable. The strength of the magnetic field, it doesn't say anything about changing the magnets. It's just we're assuming we're using the same magnets all the time here. So yeah, that it does work with this answer. So I'm going to just leave it there at B. Okay, I am going to stop here. We've talked for 36 minutes, nearly 37. So in the next video, in the next part, we're going to pick up with section B.